Okay, so these are the examples I didn't get to in class time today. My suggestion is you just look at the problem that I write up on the board and try it on your own, or pause me, and then when you worked it through, then work it out. You can watch my answer as well. So the first example for thermochemical cycles, this was example 3. Example 3. And then, so the question that I posed at the end of class was, if we know the reduction potential of iron 2 to 2 electrons goes to iron 0, and then this was the standard reduction potential was minus 0.44 volts. And then we also had the reduction potential of iron 3 plus 1 electron going to iron 2 plus. And this standard reduction potential was pretty positive. It was 0.77 volts. And again, these are half reactions, so they're referenced probably versus the standard hydrogen electrode. And then the question was, how do we know the standard reduction potential of going from iron 3 plus with 3 electrons all the way to iron 0? And so we wanted to know this standard potential. So what I mentioned at the end of class is that we can't just, unlike for electrochemical cell, we can't just add up the potentials to get to this one, because these are not opposing half reactions. So this is not a balanced redox reaction. So unlike with what we've done before, you can't just add these two together. So in this case, what we need to do is think about a thermochemical cycle. So we've drawn this out kind of as a system of equations. But so let's say this is E01 and E02, and then we would count E03. We can't add these two together, but we can add free energies. So if we call this delta G1, or G01 rather, delta G02, because these reactions balance out, we could say that this equals delta G03, and then so this has got to be equal to delta G01 plus delta G02. By the same token, we can draw this as a thermochemical cycle like we've done in previous classes. So if I were to do, let's say, iron 2 plus goes to iron 0, and then iron 3 plus goes to iron 2 plus. So this free energy going from here to here is delta G not 1, as I've written up here. This over here is delta G not 2. And then going from just from here to here is delta G not 3. So that's why we should be able to sum up delta G not 1 and delta G not 2 to then get to this pathway as well. So because of that, we can calculate our free energies from our standard reduction potentials. And so what we can do is, we know that delta G not 1 is going to be equal to negative 2F E dot 1. So this is equal to negative 2F times negative 0.44. And then delta G not 2 equals, this is a 1 electron process, so N equals 1. So this will be negative 1 F E naught 2. So this potential, which equals negative 0.77 F. This one up here is positive 0.88 F. And then so our final delta G naught 3 over here is going to be the sum of these. So this should equal 0.11 F. And then because this over here is a 3 electron process, so N equals 3 for this reduction of iron 3 plus. So this equals negative 3 F E naught 3. So therefore, E naught 3 should be equal to, we'll cross out our F's. So it's going to be 0.11 over negative 0.3. So this overall should be, whatever that works out to, it's going to be approximately negative 0.04 volts versus SHE. So in this case, again, we have to convert to delta G's in order to calculate our final reduction potential of this half reaction. So thermochemical cycles should always apply because thermodynamics should always apply. Okay, so that was the first example. I'll do the second example in a different video.